Hello physics students. Welcome to the Capacitor Discharge Lab. So at this point, you should have already printed out pages 3 through 7 of the file that I included in the Google Stream. Pages 1 and 2 you don't have to print out. As always, they are just the instructions. So if you want to print them out because you feel it'll be more convenient, you're welcome to. But again, you only need to print out pages 3 through 7. So I have the equipment set out over here, so I'm going to bring you in for a closer view. So here's the equipment we're going to be using in the lab. A couple banana wires, a stopwatch. Here's a capacitor that's approximately 470 microfarads. We've got a resistor here that's going to be over 40,000 ohms, one that's about around 3,000 ohms. We've got the breadboard to make our circuit, and a switch. 2 meters that we normally use. One we're going to be using as a voltmeter probe, so that's why we have these probe wires. And the other one we're going to be using as an ammeter, so I have alligator wires plugged in the right places. And this new meter, it is more fancy, more expensive than these. It measures the capacitance of this. We're going to be able to measure the capacitance of this capacitor. So before I show you the circuit, I think it'll be easiest to first measure the resistances and the capacitance of this of the elements we're going to be using in this experiment. So what I'm going to do is turn this on, and it can measure basically resistance, but it could also measure capacitance and something we haven't learned about, inductance, yet. So right now I have it set to measure resistance. So what I'm going to do is put this resistor on the meter, and we'll see what value it gives. Now there's a bit of a glare, so let me, maybe if I stand this up, it will be a little bit better. Yeah, so there we go. So now that's in kilo ohms, so that is 3,258 ohms. I'm going to write down that as my R1 value, so 3,258 ohms. Once again, you're going to be getting all your own data from the Google Stream in a spreadsheet that I'm going to include. So that's that resistor. Now let me measure the other resistor. This is actually auto ranging, so I don't have to change anything. It will automatically change the range. So this is 46.33, but I don't know if you could see that. That's kilo ohms again. So it's 46,340 ohms. So I will write that in for my second resistor, 46,340 ohms. And then the capacitor, I need to measure that as well. Now, so I need to first switch this over to capacitance. That's going to be inductance. One more is capacitance. There we go. Now, capacitors, many of them have a polarity. So this has to be hooked to the negative side, this to the positive, because of the structure of the capacitor. So I'll do that, and then it will measure, and it's registering 407.8, and I don't know if you could see the unit, but a microfarad right there, 407.8 microfarads. Remember, micro is 10 to the minus 6th. So I have filled in my data here. As you could see, the capacitance, the resistor 1, and the resistor 2. So what I want you to do is go ahead into the Google Stream and retrieve the data for your capacitance R1 and R2. Okay, so now what kind of circuit are we going to build? So let me show you the lab sheet. So here's the circuit we're going to build. And you see we got a voltage source right here, the switch right here, and then R1 and R2 are here. So I put 40,000, but you know, it's obviously, there's a little approximate there. So I don't remember what we had, 47, whatever it is, it's over, the larger resistor is in parallel with the capacitor. So what's going to happen, if you remember in our day when we were talking about combination circuits with the capacitors, when this switch first flips down, what will happen is the capacitor will initially act like a wire. And so the current will follow this path and go through the capacitor without going through R2. And so it'll charge the capacitor. But as time goes on, when the capacitor becomes full, after a long time, infinite time, this becomes a blockage. So rather than the current coming here and deflecting to the right and then coming down this way, it will be stopped to the right, so it'll deflect to the left. So in the beginning, what we have is a simple circuit with the voltage here, which will be 12 volts, and this 3,000 ohm resistor. That's in the beginning. And then after a long time, it's a simple series circuit with those two resistors in series. And that's when the capacitor is full. So that's the circuit I want to build so that I could analyze it. So let's take a look at how we can do that with this breadboard. So we don't need this meter. I'll shut it off and set it to the side. Oh, I'm going to unclip this. So maybe what I'll do, I don't know if you could see this, but basically what I want to do is, oh, lights are off. Let me, okay, so I wasn't moving enough. So motion lights shut off. So what I want first is the switch. So I will put that in right here. And that's going to control the electricity coming from this positive terminal. And right now this switch is open, so it cannot get to this row. But when I close it, of course, it will. So the first thing I want is the 3,000 ohm, which I didn't mention this, but I put the masking tape on there just so it's quick to identify this. And then the capacitor in parallel with that. So something like this. There, I have built this circuit. Oh, and this yellow wire now has to pick up right here. So the electricity, as you can see, can come through the switch. What did I do? I made a mistake. Okay. All right, so I forgot that I need the other resistor. Okay, jumped ahead a little bit. All right, there we are. So the electricity, when I flip this switch and close it, it can go to here through this resistor first and then branch to either of these two. Okay, but so here it is. Goes through this first and then it branches to either of those two. What I want to do is I want to insert an ammeter in there. So what I have to do is open this, and I'm just going to plug it in here for stability. But right now it's completely out, not connected to the circuit. So as of now, we just have a simple series circuit. What I'm going to do is I am now going to take this ammeter. Let me get the voltmeter out of the way so the ammeter could come a little closer. So I'll bring this a little closer, and I will complete the gap with the ammeter. So I need to connect from here to here, not by plugging it into the right place in the breadboard to make that connection, but I'm just going to go like this and like this. Now you see the electricity to get to the capacitor has to go through the ammeter, and that's basically how you set the circuit up. All right, so next thing that I'm going to do is I'm going to now connect it to the power supply with these two wires. So here's the positive terminal right there and the negative terminal right here. Now what I'm going to do is turn the power supply on, but what I want to do is get it up to 20 volts. So I will take this second meter here and connect it to the posts as we did in the series and parallel labs. Okay, now I'm going to plug this in. And I need to turn this on. And then I'm going to turn this up until I'm up to around 12 volts. All right, 12, good enough. It doesn't have to be exact because we're writing down the exact value. So 12.2, well, looks like maybe 12.3 will be the nth of the circuit. So I filled that in right there. Again, you are going to retrieve your value from the Google Stream, so go ahead and do that now. Okay. So now what I'm going to do, my circuit's all set up. And what we're going to do in the experiment, before we even do the experiment, the procedure says pre-experiment with the switch still open. What you're going to do is calculate the initial current that will come out of the power supply at the instant the switch is closed. So remember, as I said, the instant this switch is closed, this resistor is bypassed. So we just have a simple circuit that's this, okay? So it goes around like this and never goes through the 40,000 ohms. So that's what you're going to do in this space right here. Calculate the I10. So go ahead and do that now. Okay, then the next thing you're going to do is you're going to, step 7 says calculate the current that will come out of the power supply after enough time has passed for the capacitor to become fully charged. In other words, in quotation marks, after a long time. So that's what you're going to do here when this capacitor is full. Or maybe it's clearer here. When this capacitor is full, what's the current in this circuit? Okay, so that's going to go right here, I1 when time goes to infinity. Calculate that value right here. Do that now. Okay, so next thing. Step 8 says calculate the potential difference across the capacitor when it is fully charged. So that's what you do right here. Delta V capacitor. And by the way, it's not going to be the 12 volts of the power supply, because 12 volts is from here to here for the entire circuit. What does only this capacitor get over here? Well, that's what you're going to calculate right here. So maybe if you look at this diagram, again, what is this voltage right here after the capacitor is full? So do that in this space now. Okay. All right, so now what we're going to do is we're going to close the switch, and what will happen is this capacitor will gradually get full. And we could even watch what's happening in a sense by watching this ammeter. So watch what happens, okay? So I go like this, and now why is it reading this? Because there's more current. It's beyond 200 microamps, so I'm kind of like off the scale. But now the current is dropping through the capacitor. Notice how it's going down. It's exponentially decaying down to 0. So if we were to graph it, it would start like this, off the chart of the ammeter, and then gradually exponentially decay down. So we're going to wait after a long time. Now, ideally, if this were an ideal capacitor, we should read 0 amps, okay? The problem is it's not an ideal capacitor. A little too much fluctuation for my liking here, so let's see if I can get a better connection. It's not an ideal capacitor. There's always going to be some leaking charge, so it'll never get to 0. But when it's pretty stable, I don't know why it normally doesn't fluctuate around this much. When it gets pretty stable, then we can say, like now, that it's pretty much full, okay? It's stuck at that value. All right, so what we're going to do is we're going to wait 2 minutes and then measure the potential difference across the capacitor using the voltmeter. So here's my voltmeter. We calculated it, right? We already calculated it, but what is it measured? Let's see, how's the glare? Okay, good. So I go like this and I measure the voltage, and I get 11.5 volts, right? The power supply is 12.2. The capacitor only 11.5. So that's going to be the measured voltage of the capacitor. So I'm writing mine down, but you're going to retrieve yours. So go ahead and do that now. And then the last thing, you calculated it here, you measured it, you're going to calculate a percent error down here. So go ahead and do that now. Okay, so the next thing we're going to do is we're going to reopen this switch. And then we're going to actually measure the current as a function of time. So let me just flip at it. So if you see here on the next page, page 4 of the lab, which is the second sheet of your analysis, I got a data table here. We're going to be measuring the current in 10-second intervals. So it'll start high and drop to 0 because the capacitor is discharging, as we learned with capacitors charging and discharging. So why is that going to happen? Well, if we take a look back at this original circuit, so when this switch opens, there's now a gap here, and no current will go from the battery through the circuit anymore. With the gap, essentially the circuit is only this. That's the only complete loop in the circuit. This is an incomplete loop, so no electricity will flow here. So we're just going to have that capacitor discharging through this resistor, okay? And that's an exponential decay. So that's what happens when this switch opens. Now this is going to be a little tricky for me because I don't have a lab partner. Well, you're my lab partner at home, but you can't really help me. So the nice thing about this meter is it's got a freeze button, this hold. When I go like this, it locks the measurement, so I could write it down. As it's changing rapidly, I could lock it for a second and then unlock it. Okay, so that's what I'm going to do. And then, so here we go. Once I open this, I'm going to start my stopwatch, and then you're going to see that this is going to go off the scale again. But after 10 seconds, it'll go down to a value we could read again. So here we go. Ready, set, go. Okay, there it is off the scale. And you see that we're up to 8, 9, 10. Oops, 159.6. Okay. So 19, 20. Oops. Okay, so 103.1. Let me unfreeze it. 27, 28, 29, 30. Okay, so 70 exactly. And then let me unfreeze it. We're up to 36, 37, 38, 39, 40. Okay, 46.9. And then 45, 46, 47, 48, 49, 50. 31.1. Let it go. So 55, 56, 57, 58, 59, 60. So now we're up to 20.7. Okay, so 6, 7, 8, 9, 70, 14.1. Okay, 6, 7, 8, 9, 80 seconds, 9.3. Okay, and then 5, 6, 7, 8, 9, 90 seconds, 6.5. And then one last measurement, 7, 8, 9, there, 4.6 seconds at 100 seconds. So basically, as you can see, the currents dropped exponentially down for capacitor discharging. Okay, so that's that. Okay, so we're done with the data collection. The rest is all calculations. So I'll just leave this here and let the capacitor discharge down to 0. And I could shut off my power supply. Okay, so next thing that we're going to do, step 14, well, I'll put away the equipment later, but you're going to calculate natural log of the current. Now this is the current in microamps. So what you need to do is first convert it to amps, okay? So, you know, you could use scientific notation if you'd like. And then over here, you're going to calculate the negative natural log of all these values. And the reason why is because we're going to be linearizing the data. Okay, so we went over this in class, but let me show you how that's done. So, as we know, the current is equal to I0 e to the minus t over RC. Okay. Now, what I'm going to do is if I plot that, I get an exponential decay, but there's a way to make that into a straight line. And the way I could do that is take the natural log of both sides. So I'm going to have log of I on this side. And then on this side, the log of all this. Now, if you take the log of a product, you could do this. You could separate that out into an addition like this. And then this natural log of E, basically the log eliminates the E and just gives us negative T over RC. So what I'm going to do is write this way and have this, which I'll separate out like this. That's the same thing as negative T over RC. So there is how I linearize that equation, okay? So what you need to do is think about this later for the analysis. This is on the y-axis. This is on the x-axis. From the linear graph in this equation, you could see what is the slope equal to out of this equation. And what's the y-intercept equal to out of this equation? So you might want to jot this down somewhere on a scrap paper because I don't know if I'll show it again. It's going to be a little awkward. So jot that down now. Okay? All right, so the procedure says you calculate this natural log of these regular currents, and then you plot a graph over here with I and time. And of course, you know, you need your label up here, the labels here, and you plot this original current. You're welcome to stick in just microamps. You don't have to plot the regular current. So, and then you should see an exponential decay there. So go ahead and plot that on that graph now. Okay, step 17. Oh, wait a minute, I made a mistake. Okay, I'm going to have to think about editing this later. The current you plot down here. So this is going to be I, time, and then your title here and all that. And this is going to be the exponential decay. Okay, so that goes there. 17 and 18, if you look at the procedure, it says that you're supposed to plot the log of I versus time on the x-axis. Make sure to scale and label your axis and title your graph. You may create a break in your y-axis, but if you choose to do so, start the y-axis at the lowest y value rounded down to the nearest whole number minus 1. This will allow you to extend the best fit line to determine the y-intercept. If that sounds confusing, then don't make a break in the axis. Just start from 0 and, hit the camera. So 0 and go upward. So that's going to be here. You're going to get some kind of straight line over here, okay? And I believe, yeah, it goes something like this, okay? So you'll see that. So go ahead and make that plot now. And then step 18 says construct the best fit line. I did this, you don't do it freehand, you use a ruler. So construct the best fit line and make sure to extend your line to the farthest left and right extremes of the graph. In other words, make sure they hit here and here. So go ahead and do that now. 19, record the y-intercept right here. So that's off the graph. So go ahead and do that now. And 20, calculate the slope of your best fit line right here, okay? And remember that when you do that, you have to, write out your equation and all that, but also don't pick 2 points close together like this. When you calculate a slope, it maximizes the error. pick points far apart and calculate the slope, and not your data points. You shouldn't be using any of these points. You're only using your best fit line to calculate the slope. So go ahead and do that now. Okay, so let's move on. (21). Using only circuit theory and your measurements for resistance and or capacitance and or potential across the capacitor, calculate the current out of the positive plate of capacitor at the instant that the switch is open. So this is I2 at time 0, the new time 0 when I open the switch. What was the initial current? Again, you're just using equations we learned in the circuits topic. 22. Using the y-intercept of your graph, calculate the current coming out of the positive plate of the capacitor at the instant the switch is reopened. So here now you're using your y-intercept and calculating I0, here circuit theory I0. And then so go ahead and do that now. And finally, there's a place for the percent error between those two currents. Go ahead and do that now. Okay, 24. Using only resistor and capacitor circuit theory, calculate the accepted time constant. Remember, time constant is tau. Calculate what that is here. Again, not from the data I just collected, but from the measurements that we took earlier in the lab. Calculate the time constant. Do that now. Okay, 25 says using only your slope, nothing else. And so calculate the experimental time constant. So when you're all done, you're going to get another value for tau here. Okay? So go ahead and do that now. And 26, calculate the percent error between these two values right here. So go ahead and do that now. Okay. Moving on. 27. Using the graphically determined, in other words, the experimental time constant and the graphically determined initial current, write an equation for the current coming out of the capacitor's positive plate as a function of time. So when you're all done here, you should have I equals, and then a function of time, any number in that equation, or all the variables in that equation have to be replaced with numbers, which you determined in the theoretical data, the experimental data, okay, for time constant and initial current. All right, so that's what you put there. So go ahead and write that equation now. 28, using only your expression for current as a function of time and a math procedure for finding the total charge from a non-constant current, determine the experimental total charge that was initially stored on the capacitor's positive plate. So you're going to be using this, and somehow when you're all done, you're going to get the charge as a number, some number of coulombs, or you could have microcoulombs if you want, whatever, but it's going to be a number, not an algebraic expression. And you're going to be using this equation. So go ahead and do that now. 29, using the equation between C, delta V, and Q. Determine the theoretical charge that was initially stored on the capacitor's positive plate. Use the calculated delta V in your calculation. In other words, that was from step 8, okay, of the calculation. Go ahead and calculate that charge now. And then the last thing, 30, you do a percent error between these two charges. So go ahead and do that now. Okay, so that is the experiment, the calculations. What you're going to have to do now is finally answer these questions. In number 1, what you're doing is you are sketching different graphs, okay, for situations like number one, the graph to the right shows the plot of C0, V0 discharging through R0. Using a colored marker, sketch the graph of a capacitor with 2C0 at the same original voltage and the same original resistance. So maybe, I don't have a color, I have my pencil, but maybe I think it's a sine graph. It's not, but maybe I think it's that, and then I go like this, right? And then the next one, using a unique marker, sketch C0, V0, but this time twice the resistance. So maybe this was like a purple marker, and this is going to be like a green marker, and it's a parabola, so I call this green. All right, so, again, these are wrong. But you're going to, sketch these three different scenarios and be mindful of the original current and the time constant, and try and as accurately draw the changes as possible. The light is being very stubborn. All right, so, and 4, color the legend. All right, and then just a couple questions here that you need to answer. Think about them carefully and write them out. So that is the question page. Okay, so that was the Capacitor Discharge Lab. I hope you enjoyed it. As always, submit photos of the last 5 pages, your work, your calculations, and your conclusion questions in the Google Classroom stream, and I'll see you in the next physics video.